So let us do methods of proof. So for methods of proof, we will first discuss the so-called direct proof. So the direct proof is of the form P implies Q, where P be what we call the hypothesis and Q be the conclusion. So the process for direct proof, so we assume that the hypothesis uh, would be true. Then after some manipulation, we need to arrive at the conclusion Q. So for example, let us prove this theorem. So prove that for A, B, and Z be subsets of the universal set, if A is a subset of B and B is a subset of C, then A is a subset of C. So for this statement, P here would be A subset of B and B subset of C. And then the proposition Q would be A subset of C. So this statement is of the form P implies Q. So given the hypothesis P, we need to arrive at the conclusion Q. So let us do the proof. So suppose X be element of the set A. So we need to show that this element X must also an element of the set C. Now, by hypothesis, we may say that X is element of B since A is a subset of B. Now also, since B is a subset of C, we have X element of C. So hence, we arrive at the conclusion A subset of C. So to end the proof, we may use this symbol or the acronym QED to end the proof of the theorem. So next comes the indirect proof. So in indirect proof, we have the so-called contrapositive and we have contradiction. So for the contrapositive, in logic, P implies Q is logically equivalent to not Q implies not P. Now, this statement is what we call the contrapositive of the statement P implies Q. So for us to prove that this statement using contrapositive, we will use this proposition. And then for contradiction, P implies Q is logically equivalent to not Q and P implies a contradiction. So for example, let us prove that if x squared is odd, then x is odd. So we will use contrapositive to prove the statement. So let's have the contrapositive of the statement: if x squared is odd, then x is odd. So you know that the proposition P would be x squared is odd, and the proposition Q be x is odd. Now let's have not P. So if x squared is odd, if we do not P, that would be x squared is not odd. That means x squared is even. And then not Q. So if Q would be the proposition x is odd, not Q is the proposition x is even. So we will now prove not Q implies not P. So that is, if x is even, then x squared is even. So let us do the proof. So suppose x is even, then by definition we may write x be 2k, where k be element of the integers. Now taking the square of x would be 2k squared, so that is simply 4k squared, and then this 4k squared can be written 2 times 2k squared. If we let q be 2k squared, we see that q is an element of the integers. K is an element of the integers. If we square that, it is also an integer. If we multiply it by 2, it is also an integer. So hence, x squared equal to 2 times q, which is also even by definition. So we may end the proof. Okay, so for the next example, we will prove this by contradiction. So show that there is no positive integer that is less than 1. So let us do the proof. So we suppose there is a positive integer that is less than 1. So namely a. So a is less than 1. So since a is greater than 0, I use the hypothesis that we have a positive integer. So a positive integer is always greater than 0. So we have a times a less than a times 1, which simplifies a squared less than a. Now, this statement is a contradiction. So we may end the proof. Okay, so let's have proof by cases. So proof by cases is of the form P1 or PQ or up to Pn implies Q. Now, this statement is logically equivalent to P1 implies Q and P2 implies Q, and until we reach Pn implies Q. So to prove this statement, we need to show that each of these proposition must be true. So for example, let us prove that for all x, y be element of the set of real numbers, if we take the maximum value of x and y plus the minimum value of x and y, we arrive at x plus y. Okay, so let's have the proof. So for the proof, we have two cases. So case 1 would be x less than y. So if x less than y, if we take the maximum of x and y, so the answer is y, and the minimum of x and y would be x. So hence, the maximum of x and y plus the minimum of x and y would be y plus x, which is also equal to x plus y. So let's have case 2. So for case 2, we have y less than x. Now, if we take the maximum of x and y, so that would be x, and the minimum of x and y would be y. So hence, the maximum of x and y plus the minimum of x and y would be x plus y. So thus, in either case, maximum of x and y plus the minimum of x and y is equal to x plus y. So end of the proof. So we also have existence proof. So in existence proof, this statement, so we read this as for all x p of x. So this statement must also be true. Another one, we have this statement. So it reads, there exists x such that p of x is true. So for example, show that there exists p element of R such that p is between x and y, where x and y be elements of the set of real numbers. Okay, so let's have the proof. So since x is less than y, we have 2x less than x plus y, and x plus y is less than 2y. So hence 2x less than x plus y less than 2y, and x is less than x plus y all over 2 less than y. So we choose p be equal to x plus y all over 2. So that's the end of the proof. So next we have mathematical induction. So we usually use mathematical induction in proving theorems for all n element of the positive integers. So the idea of the mathematical induction is this. So suppose we have a proposition p of n is true, then we need to prove the proposition p of n plus 1 must also be true. So for example, let us prove that for all n element of the positive integers, the sum 1 plus 2 plus 3 plus up to n is equal to n times n plus 1 all over 2. Okay, so let's have the proof. So usually in mathematical induction, we start at verification. So we have verification. So I'll just verify the proposition for n equals 1. So if we have p of 1, so we have 1 equals 1 times 1 plus 1 all over 2, which is 1. So the proposition is true for n equals 1. Now, for inductive step, so we suppose p of n is true, then we need to show p of n plus 1, which is 1 plus 2 plus up to n plus 1, so equals n plus 1 times n plus 2 all over 2, is also true. Now, since 1 plus 2 plus up to plus n plus 1 is equal to 1 plus 2 plus n plus n plus 1. So this term is simply p of n. So we may use the proposition for this expression. So we have n times n plus 1 all over 2, and then plus n plus 1. and then we just manipulate this. This will be n times n plus 1 plus 2 times n plus 1 all over 2, which gives you n plus 1 times n plus 2 all over 2. So hence, p of n plus 1 is also true. So for other proof techniques or methods, let's have this. So how to prove uniqueness? So let's take this example. So prove that in R, the additive in identity is unique. So for the proof, we suppose we have 0 and 0 prime be two additive identities in R. Then we may write 0 plus 0 prime equals 0. So for this statement, 0 prime is the identity or the additive identity and then we also have 0 prime plus 0 equals 0 prime. So for this statement, 0 is the additive identity. So hence, we may write 0 plus 0 prime equals 0 prime plus 0, since addition is commutative. So thus 0 equals 0 prime. So end of the proof. And then for the last, we have the proposition P implies Q1 or Q2. So in logic, P implies Q1 or Q2 is logically equivalent to not, this is Q1, not Q1, and P implies Q2. So for example, let us prove, let A and B be any two real numbers such that A times B equal to 0, then either A equal to 0 or B equal to 0. So let's have the proof. So suppose A is not equal to 0, then we may write 1 over A times B equal to 1 over A times 0. So here I just multiply 1 over A to both sides of the equation. And then by the associative and identity properties, of the set of reals, we will have 1 times B equal to 1 over A times 0. Hence, we have B equal to 0.